The other kind of magnetic material is ferromagnetic. Third. What was the difference between diamagnetic and paramagnetic materials? At the atomic level, what was the difference? Anyone?
Paired and unpaired electrons.
What did you say?
Paired and unpaired electrons.
In terms of electron pairing, diamagnetic materials at the atomic level itself, there is no dipole moment. Okay. But for paramagnetic materials, atoms behave as dipoles, but the object as a whole doesn't exhibit magnetism because all the dipole moments get cancelled. They are randomly aligned, so they'll almost get cancelled, or even if they are not cancelled, it will be a negligible amount of magnetism on its own. When you put it in an external field, it gets magnetized. That is a different case. Okay. Now in ferromagnetic substances, what happens is at the atomic level, there is dipole moment. And you see the atomic dipoles arranged somewhat like this. In ferromagnetic substances, there are something called domains. Now, what is a domain? Domain is a region in which all the atomic dipoles, okay, at the atomic level, there is dipole moment. So unpaired electrons are there. All the atoms with those unpaired electrons, they are aligned in the same manner. Okay, but that doesn't happen all over the object. There are some microscopic regions in which that happens. Okay, so we call this as one domain. Similarly, there will be other domains as well. This is another domain. You can call this as another domain. So in this case, I'm showing you 3 domains. Of course, there will be millions and millions of them. In a particular domain, all the atomic dipoles are aligned. But domain to domain, the alignment can vary. So this is what happens in ferromagnetic substances. When there is no external field, internal field also will be 0. Okay, because the field created by one domain can be cancelled by field created by the other domains. Fine. So domain-domain relation is not there. There will be millions and millions of domains. They'll all cancel. That is what happens in ferromagnetic materials. Now, when you place this ferromagnetic material in an external field, let's say the external field is to the right. You will see these dipoles in the domains start getting aligned. Starting to get aligned in the direction of external field. They'll more or less tilt towards the direction of external field. So some of them may get perfectly aligned. Because the first domain, if you see, they were already tilted to the right by a significant amount. So when you switch on an external field, they may get completely aligned to the right. That possibility is there. Now the second one, they are tilted like around 11 o'clock, 10 o'clock, 11 o'clock angle. They'll tilt somewhat to the right in the direction of external field. Situation will be like this. That is one domain. And the third one, they'll tilt more to the right. Situation will be like this. Okay. So now the domains have a preferred direction of alignment. So they are more or less tilted in the same direction as the external field. So what happens is internal field gets produced in the same direction as the external field. And because internal field is in the same direction as the external field, the net field will be very strong. And net field is very strong, so the field lines will have to come close to each other near the magnet. Situation will be like this. Okay, those are the magnetic field lines around a ferromagnetic substance. Is this clear to all of you? Any doubts in this? Yes, tell me.
Sir, initially when B external is 0,
Hmm.
the domains will be in some random direction, right?
Domain to domain direction
Yeah,
will be
domain to
random.
domain.
Yes.
Okay.
Huh. One complete domain will be aligned in the same direction. That's why it's called a domain. But from one domain to the next domain, the alignment will be random. Any other questions? Okay. Now we know that net field is the vector sum of external plus internal fields. And you know internal field is x times of external field, where x is susceptibility, x or chi. So we write this as 1 plus x times of B external. Right. And you can tell this also. Internal field is chi into external field. Now internal and external are in the same direction in a ferromagnetic substance. For internal external to be in the same direction, should susceptibility be positive or negative? For these two
Positive.
vectors to be in the same direction, the proportionality constant between them should be positive. And in case of ferromagnetic substances, it is a large positive value, usually greater than 1. Okay, just a moment. Let me take an example value. Magnetic susceptibility of ferromagnetic materials is in the range of 1000 to 10,000, positive and very high. Okay. So the internal field that they produce is about 1000 times to 10,000 times stronger compared to the external field. So they produce very strong magnetic fields. Fine. Next is the dependence of susceptibility on temperature. Now, one of you recollect and tell me, how does susceptibility of diamagnetic materials vary with temperature? Diamagnetic. Okay. For diamagnetic materials, susceptibility is independent of temperature. For paramagnetic,
Sir, it increases with the alignment.
what
Decrease.
Like
increases?
increases.
Susceptibility increases if temperature increases.
No, sir, it's
No.
inversely
No,
proportional.
the more the temperature, it like more disturbs the inside thing, so it'll be less.
Yes, yes. You told the explanation. I mean, you told the reason also. Greater the temperature, greater will be the vibrations, and vibrations disturb the alignment. Okay. So susceptibility, the internal field produced will become weak, susceptibility will be low. So if temperature increases, susceptibility decreases. Paramagnetic substances, they are inversely proportional if temperature is in the Kelvin scale. Okay, remember that also. In questions, they can just give you temperature in degree C and ask you questions based on it. You'll have to convert it to kelvins and then solve. Okay. When it comes to ferromagnetic, as such, the exact relation between temperature and susceptibility is not established. But in ferromagnetic materials, there is a temperature called a Curie temperature. TC. What is Curie temperature? The temperature above which a ferromagnetic material converts into a paramagnetic material. Okay, so the temperature above which ferro changes to para. What is the difference between ferro and para magnetic substances? Domains. Okay, in paramagnetic and ferromagnetic, at the atomic level they are dipoles, but in paramagnetic, atom to atom, the alignment is random. In ferromagnetic materials, domain to domain, the alignment is random, but within a domain all atoms have the same alignment. Now when you raise temperature, what happens? No, this domain nature will get disturbed. Okay, so within the domain also alignment will be gone when you raise temperature beyond the Curie temperature. Okay, that depends on material. All ferromagnetic materials don't have the same Curie temperature. It changes from 1 to 1. Okay, but basically beyond a certain temperature, what happens is domains get disturbed, or domain, what should I say? Intra-domain means within the domain. Yeah. Intra-domain alignment is disturbed. You can say it becomes random. Within a domain itself, if it becomes random, effectively it is changing into paramagnetic. Everywhere it is random. Okay, so Curie temperature is the temperature above which ferro changes to para. Once the temperature is more than the Curie temperature, the susceptibility will be inversely proportional to 1 by T minus Tc. But remember, this is valid only when the temperature is more than the Curie temperature. Means when it changes to para, then you can use this. So basically that ferro behavior, the domain behavior will be lost. Is this clear to all of you? Nothing much. If you raise the temperature, the domains will get disturbed. They'll be randomly aligned. So the whole object will become randomly aligned like a paramagnetic substance. That's all. Okay. Now you all tell me, if a ferromagnetic substance, or if we bring a magnet near a ferromagnetic substance, what will happen? Suppose this is ferromagnetic. You bring a magnet close to it. What will happen? The answer won't depend on which pole is brought closer, but just for us to visualize, let's take it like this. Think carefully and answer. Seshank, how are you trying to answer this? On what basis will you tell what will happen?
So initially I thought it would attract, but then you said it's independent of which pole is brought forward, so I'm confused.
So you're saying North Pole would attract, but South Pole would repel.
No, I thought there will be like poles repel, unlike poles attract kind of situation.
That is always there. Like poles repel, unlike poles attract. So you are saying answer will depend on which pole is brought closer to the ferromagnetic material.
Yeah, that's what I thought, but then you said that's not the case. So now I
What made you think like that? Like suppose North Pole is brought as shown in this diagram. And let's say I did not tell you that it is independent of which pole is brought. How would you answer? Okay, let it be. Yes, what do you say will happen? Attraction, repulsion, nothing.
Sir, can you show that upper diagram? Like, can you scroll a bit? Yes, so this is for ferromagnetic, right?
Yeah, this is for ferromagnetic.
So, like all the domains will get like aligned with the
External
magnetic
field.
field here.
Hmm.
Yeah. So, no idea. Sir.
Okay. Isha, any answer? Manasa.
No ideas.
Why is it so difficult to answer? Okay. What will the magnet do? What does any
It will
magnet
create a
do?
magnetic field.
It creates a magnetic field. In which direction will the magnetic field be in this case? I mean, the ferromagnetic material, it will experience the magnetic field of the bar magnet. In which direction will that field be? Okay, wait. I'll show you all the field lines of a bar magnet. Just a moment. Earlier, there used to be an experiment based on this. Okay, like you take a big white chart that what size is that? A4, A3, A2 size chart. You keep a magnet on it. You put iron filings all over the sheet, and then you tap the sheet. The iron filings will align themselves in the direction of the field lines. You can literally see magnetic field lines. Okay. See here, within the magnet, they have not drawn, but inside the magnet, the field will be from south to north. Magnetic field lines form closed loops. Actually, no, this is not a proper diagram. Just a moment, I'll take another diagram. Yeah, this one is better. Just a moment. Just delete this. Yeah, you can see that they are all complete closed loops. Outside the magnet, the field lines go from north to south. Inside, they go from south to north. All field lines will be like that only. That is how the magnetic field lines of a bar magnet look. The same field pattern you will see in a solenoid also. Okay. Solenoid is basically a spring-like coil. We had discussed that. Field produced by a solenoid and field produced by a bar magnet are identical. Situation will be like this. You can call a solenoid as an electromagnet also. Because when current passes through it, it produces the magnetic field. When current is switched off, the magnetic field also gets switched off. Okay. Anyway, you see, near the north pole, outside the magnet near the North Pole, field will be away from the magnet. And outside the magnet near the South Pole, field will be towards the magnet. Now what we did was we placed the ferromagnetic substance here. Okay. So you can see there are field lines. This is the external field. I'm just changing the color. So the ferromagnetic substance is in the presence of an external field now. And that field is roughly directed to the right, not exactly to the right, but roughly to the right. So tell me, in which direction will the internal field get produced inside the ferromagnetic substance?
In the same way.
In the same direction as the external field. Okay. That means field will roughly be to the right. If field is to the right, what happens inside the ferromagnetic substance is, on the right side, you will see a north pole developing, and on the left side, you will see a south pole developing. Because inside the magnet, field has to be from south to north. No, you know field is going to be to the right. So it has to be from south to north, means left side is south, right side is north. Now tell me, will the ferromagnetic material get attracted to this magnet or repelled by it, or nothing will happen?
Attract.
It will get attracted. Okay. Like, see, external field is to the right. South pole is like negative charge, north pole is like positive charge. Negative charge experiences force opposite to the field. Positive charge experiences force in the direction of the field. But negative charge is in the presence of a stronger field. You can see the density of field lines there. It's more. Okay. So what will happen? Attractive force will be greater than the repulsive force. The material gets attracted to the magnet. Now let us reverse the situation. Let us like change the orientation of the bar magnet. Bring that ferromagnetic substance and put it here. Tell me the answer, all of you. What will happen to this ferromagnetic substance now? You can imagine field lines. This time the field lines are roughly to the left. What will happen inside the ferromagnetic substance? And as a result, will it get attracted or repelled? Mansa, what do you say?
Sir, mostly they will get repelled.
Why? What will happen inside the ferromagnetic material? External field is to the left. Anyone? External field is to the left. What happens inside the ferromagnetic material?
It will get attracted.
What happens inside the material?
Like the dipoles get arranged in with the direction of magnetic field.
The dipoles get aligned in the direction of external field. See, in the explanation also, the external field, when it was to the right, the dipole alignment also was more or less to the right. Internal field was to the right. External field, if it is to the left, then internal field also will be to the left. Okay, because external field is what dictates what happens inside. So in this case, the field lines passing through the material are more or less to the left. So internal field will be to the left. If internal field is to the left, inside a magnet, the field should be from south to north. It means this side will be south pole. This side will be north pole. North experiences force in the direction of the field. South experiences opposite to the field. And near the North Pole, the field lines are close, means field strength is more. So attraction will be stronger than repulsion. It will still get attracted. Are you all getting this, or is there any confusion? Ask if you have
No,
any
sir.
questions. In both cases, the ferromagnetic material will get attracted only. Shashank, are you convinced?
Yes.
Huh. Okay. Diamagnetic substances are the only ones which get repelled by magnetic fields. Para and ferro, they get attracted. Okay. And here also, why is attraction happening? Because North Pole is experiencing a stronger external field than the South Pole. If you put it in a uniform external field, the attractive force and the repulsive force will cancel. Net force will become zero. It will not move at all. Okay. So generally you can say para and ferromagnetic materials tend to move from regions of weaker magnetic field to regions of stronger magnetic field. Like in this case itself, ferromagnetic, it is getting attracted to the magnet, no? So it is coming to a region where the field is very strong. Closer to the magnet field will be strong. So it tends to go to a region where the field is strong. Yash is saying examples of ferromagnets are iron and nickel. So however the pole of magnet, it will, yes, iron is an example of a ferromagnetic material. Irrespective of which pole of the magnet you take to it, iron will get attracted to the magnet. You all must have experienced this. Okay, so yeah, that is what happens. But remember, if they want to ask you in depth, they'll ask you what will happen if it is in a uniform magnetic field also. If it is in uniform magnetic field, the attractive force on the North Pole will be equal to the repulsive force on the South Pole. Then the net force on the magnet will become zero. This is true for any dipole, even in electric dipole case. If the electric dipole is in a uniform external field, then force on negative charge, positive charge will cancel. If it is in non-uniform external field, they may not cancel. Net force can be non-zero. Same thing with magnets. Is this clear to all of you? Okay. And see, ferromagnets, as we discussed, they produce a very strong internal field, which is about 1000 to 10,000 times stronger than the external field. Now, once you remove the external field, what do you think will happen? Will the domains go back to random alignment, or will they maintain their alignment? Once we magnetize it by using an external field, if you remove the external field, what do you think will happen? Just try to guess. Will the alignment be gone, or will it still be there? Shashank, what do you think?
Still, it will be this.
Okay. Once magnetized, even if we switch off the external field, the material still behaves as a magnet. Means it will not go back to random alignment. More or less, the domains will stay aligned like that. So you can make permanent magnets using ferromagnetic materials. Magnetize them once, they will be magnets. Okay. So permanent magnets can be made from ferromagnetic materials. Okay, they tend to retain their magnetism. Of course, you can demagnetize also. Now see, we applied external field to the right, so internal field alignment was to the right. You remove external field, this alignment will stay. Okay, may not be 100%, but more or less it will stay. Okay, so what happens? This side behaves as south pole, this side behaves as north pole. You have a magnet now. Okay, the unmagnetized object is now magnetized. But this thing, this magnetized ferromagnet, if you put in an external field which is opposite to internal field, then you can demagnetize it, because now the domains will tend to tilt in the other direction. Okay, you can remove that magnetism also. You can demagnetize materials. Sashank is saying there was a method of magnetization we learned in lower classes where you rubbed a bar magnet in a certain way against a metal to magnetize it. Yeah, they rub a magnet against another metal and magnetize it, correct? Is that temporary or permanent? That is permanent. Anyway, it depends on the material actually, but usually they do it with iron. Okay, you take a permanent magnet and keep rubbing it against iron. That iron thing will get magnetized. Okay, basically, whenever you rub the permanent magnet against iron, no, a little bit of alignment happens. Next time you rub it, some more alignment. Rub it once again, some more alignment. So as you rub it over and over, what happens is alignment becomes stronger and stronger. The iron piece becomes a magnet. Okay, but they can be demagnetized also by applying an external field opposite to the magnet. Can be done. Earlier in your syllabus, there was this property of ferromagnetic substances called hysteresis. Now it is not there. Okay, so basically hysteresis is like that only, the ability to retain magnetism. Anyway, we'll not get into all that. So remember, ferromagnetic materials can be used to make permanent magnets. Okay, once magnetized, they tend to retain that magnetization. Okay, so any doubts? Ferromagnetism.
So can you show that once magnetized, that statement once?
Once
Yes, sir.
magnetized, even if we switch off the external field, the material still behaves as a magnet. Yes.
And also the permanent magnets also. It's
Just permanent magnets can be made from ferromagnetic.
oh, okay, sir. Yeah.
Okay. Right. So these are the three magnetic materials: dia, para, and ferro. Learn about the individual differences. Learn about susceptibilities. Learn about how susceptibility depends on temperature in each case. In case of ferromagnetic materials, we talk about Curie temperature also. Okay. Go through all this once. Next thing we have in this chapter is, yeah, that field lines of bar magnet was there. We have seen that anyway. Now, the main difference between electric field lines and magnetic field lines is that magnetic field lines always, there is no exception to this, form closed loops. We had discussed this in the last chapter also, moving charges and magnetism. We drew field lines around a current carrying wire. Okay, they always form closed loops. Okay. Let's consider that bar magnet once again. Can one of you quickly tell me Gauss law in electrostatics? Or at least the equation of Gauss law.
Integral b bar dot ds bar is equals to q by epsilon.
E, electric field, okay? Closed integral E dot ds, ds or dA you can write, is equal to charge enclosed divided by epsilon naught. What is the meaning of closed integral E dot dA, anyone? What is E dot dA?
Flux.
Electric flux, correct. So closed integral E dot dA is the net electric flux through a closed surface. Closed imaginary surface, we call that as a Gaussian surface, okay, is equal to charge enclosed by divided by epsilon naught. Now one of you tell me, what is flux a measure of? What is
Number of
flux?
field lines passing through a unit area.
Not unit area, through area, okay. Flux is a measure of field lines passing through a surface, okay, fine. So that electric flux, if you want, you can tell based on the enclosed charge, okay. Now let us talk about magnetic flux through a closed surface. Imagine a closed surface here, all of you. I'll take three different surfaces. Let's take one surface on this side. Let's call it S1. Let's take one surface like this, enclosing one pole of the magnet. Let's call that surface as S2. Okay, we'll take them one by one. Let's say this is the first surface. It's a closed surface, as you can see. Now, flux is a measure of field lines. If field lines enter into a closed surface, it is counted as negative flux. And if field lines leave a closed surface, it is counted as positive flux. Now you all observe this surface and tell me the number of field lines entering into it and the number of field lines leaving it, are they equal or not?
Yeah.
Do all of you agree that number of field lines entering is equal to number of field lines leaving?
Yes, sir.
Yes, why are you saying no? How, count
So
and
in
tell
this
me.
surface only,
How
it
many
is
field?
near the South Pole, right?
Let it be.
So here they are just entering, no? Like as we can see.
How can you? They are entering into the magnet. For the surface, you see, I'll mark some points in red. This point, this point, this, and this. These are the points from where the field lines are entering into that closed surface. On the other side, they are leaving. No, I'll mark them in green. Do they look like they are leaving from those green points or not? They're going out of the closed surface.
So yes, got it.
Okay, these purple dots. There the field lines are going out of the surface. So number of field lines entering is equal to number of field lines leaving. Then tell me, what is the net magnetic flux through the surface S1? Closed integral, like E dot dA is electric flux, B dot dA is magnetic flux. We'll be using that more in the next chapter, electromagnetic induction. But tell me, what is the net magnetic flux through the surface S1?
0, sir.
0. Because the number of field lines entering is equal to number of field lines leaving. Negative flux is equal to positive flux. Net flux becomes 0. Okay. Now let us imagine a surface enclosing one pole of the magnet. Because there were no poles enclosed by the surface S1, maybe that's why the flux was 0. We don't know. But let's take a surface now enclosing one of the poles. Consider this surface, all of you. See and tell. Number of field lines entering, number of field lines leaving, are they same or not?
No.
Why did you say no? Are the number of lines entering more or the number of lines leaving more?
Leaving.
Why? Okay, Sashank, you are saying number of lines leaving is more than the number of lines entering, it means, okay, others also listen. If number of lines leaving is more than number of lines entering, it means some new lines are being created inside the surface. Yes or no? Suppose 10 lines entered, but 12 lines are leaving. It means 2 new lines were created somewhere. Seshank, you tell me, where are the 2 new lines? Where do you see 2 new lines getting created? Field lines. Is there any point of origin of the field line here? See, they have just written N and S, but you imagine that N and S to not be written there.
The field lines appear to be originating from the end of the line.
What did you say? The field lines?
Appear to be coming from the end of the line. Yeah. Where the North Pole is not.
Are there no field lines inside the bar magnet?
Yes.
Is the number not the same? Are they getting created newly anywhere?
Oh, okay. Yeah. The number is.
Others also, are you all convinced or not? Number of field lines entering is equal to number of field lines leaving. I'll show you a better diagram. Let's use this. This is the closed surface. It is enclosing one of the poles of the magnet now. Okay. Now we can clearly mark the points where the field lines are entering. I'll mark them in black. There's one line entering here. Okay, like arrow. Inside the bar magnet, the field lines are to the left. All the field lines are to the left inside the bar magnet. Outside, they are from north to south, so they are going to the right, more or less. Anyway, 1, 2, 3, 4. This fifth one is a straight line. 6, 7, 8. 8 field lines are entering into this orange surface. Leaving, if you see, I'll mark them in blue. 1 is leaving here itself. 2, 3, 4, 5 is the straight one. 6, 7, 8 field lines are leaving it. Number of field lines entering is equal to number of field lines leaving. You can use this logic also. If number entering is not equal to number leaving, it means the field lines are terminated or are originating somewhere inside the surface. But you all look at the field line pattern and tell me, do you see any starting point and ending point for any of these field lines? Is there a point of origin and a point of termination? Or are they continuous loops?
No, there's no point of it.
There is no point of origin or termination for these field lines. Yesh, what is your doubt?
Sir, like, how is this surface placed with respect to that bar magnet, sir? Like, I'm not getting it.
How do I show you? Okay. I have one biscuit packet here. Imagine this as the closed surface, okay? Closed biscuit packet, closed surface. Let's say this pen is the bar magnet. This tip of the pen is the north pole. The surface is enclosing the north pole. It's like this. Okay.
So, like, it's enclosing a volume set.
Of course, it's a closed surface. Closed surface encloses a volume. Yes. It's not a closed
No,
loop.
I just thought that it is a like a flat.
No. It's like a balloon. Okay. It's not a closed loop. It's a closed surface.
Okay.
Okay. We are not talking about Ampere's law. We are talking about Gauss law. Okay. Ampere's law would have been closed integral B dot dl. That is different. Okay. Remember all of you, these are 3-dimensional surfaces that we are talking about. Okay, like literally you can take it as a balloon. One pole is inside. Okay, but anyway, you see that there are no points of origin or points of termination for magnetic field lines. They are always closed loops. A closed loop will not have a start or an end. Okay, that means number of field lines entering any closed surface should definitely be equal to the number of field lines leaving that closed surface. There is no other possibility, irrespective of how you take the surface, whether you take the surface like this, completely outside the surface, whether you take the surface like this, enclosing one pole of the magnet. You can even take the surface like this, enclosing both poles of the magnet. Whatever be the surface, whichever way you take the surface, if it is a closed surface, field lines entering will be equal to field lines leaving. Net magnetic flux through a closed surface is always 0. Okay, so that is Gauss law in magnetism. Mathematically, it is useless. Okay, in electrostatics, at least we used Gauss law to find out the net flux through a surface or to find out electric field in some cases, because the right hand side is non-zero. In magnetism, closed integral B dot dA is always 0. You can't use this to derive magnetic field. Okay, we use Ampere's law to derive magnetic field. So this is Gauss law in magnetism. Okay, very simple. Closed integral B dot dA is 0. Why is it 0? Because magnetic. Okay, you all tell me. What is the exact reason? Why is magnetic flux through a closed surface always 0?
Like there is no starting or terminating point.
Correct.
And also the negative and minus of the flux get cancelled in.
Yeah, and like both of them mean the same thing effectively. Magnetic flux, or I should say net magnetic flux through a closed surface is always 0, because magnetic field lines form closed loops. So there's no point of origin or point of termination. So number of lines entering should be equal to number of lines leaving. Okay. Yeah, effectively, that is all there is in this chapter. Nothing much. You may be asked questions based on multiple magnetic dipoles, like 2 bar magnets. Okay, let's take one question. Remember, bar magnet is a magnetic dipole. It has a south pole, north pole. It's a magnetic dipole. Okay, and you can treat it in the same way as you treat electric dipoles. Okay, let us discuss that first. Just a small point. Electric field of electric dipole and magnetic field of magnetic dipole are analogous. What do we mean by this? Suppose there's an electric dipole with its center at the origin, dipole moment P. One of you quickly tell me, on the axial line, what is the electric field produced by an electric dipole? How much is it? 2k P by r cube or x cube. Okay, let's write it as r cube itself for now. And it will be in the same direction as the dipole moment, like this. Anywhere on the equatorial line, can one of you tell me how much is the field it produces? Quick. Okay, it'll be minus kp by x cube. So its direction will be opposite to the dipole moment. Okay, why is it like this? See, we had discussed electric field lines, charges and fields, no, long back. Okay, just a moment, I'll show you the diagram. Electric field lines of equal and opposite charges. Okay, one is negative, one is positive, as you can see. So basically this is a dipole. The dotted lines indicate the equipotential surfaces, ignore them. For an electric dipole, on the axial line, the field will be this way. On the equatorial line, you can see here, the fields are all opposite to the dipole moment. Okay, this being the equatorial line. Perpendicular bisector basically. Okay, axial line, it will be in the same direction as the dipole moment. Equatorial line, it will be opposite. And if you see the field pattern, the field produced by bar magnet and the field produced by electric dipole, they are almost the same. As I said, south is like negative charge, north is like positive charge. So you can see how the field lines are going from north to south. Only difference will be inside. Okay, for electric dipole or in case of electric charges, the field lines are always from positive to negative. In case of a magnet, inside the magnet, there will be a difference. They'll be from south to north. But anyway, we are talking about field outside the magnet, no? So once you go outside, the behavior of electric dipole, magnetic dipole is the same. Okay, so for an electric dipole at the axial point, it is 2 kp by r cube. Equatorial point, it is minus kp by x cube. Similarly, for a bar magnet also you can write. Just a moment. In bar magnet, as I said, you treat north pole as the positive charge, south pole as the negative charge. So consider this situation. South negative, north positive. So the dipole moment is this way. Magnetic dipole moment. And if you take an axial point, can one of you tell me what the expression for the field will be? For electric dipole, it was 2 kp by x cube, where k is 1 by 4 pi epsilon naught. So you write it as 2 into 1 by 4 pi epsilon naught p dipole moment divided by x cube or r cube, anything you can write. When it comes to a magnet, what does k change into? In electrostatics, k is 1 by 4 pi epsilon naught. In magnetism, in place of k, what should you write? We had discussed this in the last chapter.
Mu0 by 4.
Ha. 1 by epsilon naught changes to mu naught. Okay. So the axial field, magnetic field produced on the axis will be 2. In place of k, which is 1 by 4 pi epsilon naught, you write mu naught by 4 pi. That is k. In place of electric dipole moment P, you get magnetic dipole moment M, and cube of distance stays as it is. That's all. Whatever formula you have for electric dipole, same formula you can write for magnetic dipole. Terms you have to adjust. And if you see on the axial line, the field is opposite to the dipole moment. Fields are like this. And axial field will be, wait, not axial, sorry, equatorial. That is axis, this is equatorial line. Equatorial field will be minus, there's no 2, just kp by x cube, no? So minus, in place of k, you have mu naught by 4 pi. In place of p, you have m divided by r cube. That's all. So you can be asked questions based on this. The magnetic field produced by a bar magnet or a combination of bar magnets. Is this clear to all of you? Any doubts in this? Okay, fine. Then that is all there is in this chapter. One of the very short chapters that you have in 12th class. In 12th, actually, the biggest chapter was the last one only, I think. Moving charges and magnetism. And after that, you have ray optics. That is one very large chapter. Other chapters are all very small. Okay, anyway, Tuesday's class, we will start electromagnetic induction, Faraday's law applications, if possible, Lenz's law also. And tomorrow I will send you a worksheet based on this chapter, you solve it. So main thing you need to remember in this chapter is dia, para, ferro, how they behave, and what is susceptibility, how it is related to relative permeability, okay, that we derived in the last class. Relative permeability is 1 plus susceptibility, that is permeability of the medium divided by that of vacuum. So for any medium, you can write permeability as mu naught into 1 plus x. And then magnetic field of a bar magnet, magnetic dipole. Okay, thank you all. We'll close the session here. We'll continue on Tuesday.